Welcome to Data Science 1, Probability, the chi-squared distribution. Okay, so things we're going to need to remember. We're going to need to know what the sample space is, a random variable, cumulative distribution function, probability density function, and the standard normal distribution. Okay, here's the setup. Suppose we have z distributed as a normal with mean 0 and standard deviation of 1, and this is how we could write that out. And the density is given by this function here. Okay, so this is one of the building blocks of other probability distributions. So when I talk about building blocks, don't think about it like we've looked at the other ones where we were specifically interested in an experiment that gave us this particular random variable. Here, we're going to want to know this random variable because it shows up in other formulas and we want to know the distribution of other formulas. So consider the following simple transformation. X equals z squared. Okay, so I'm going to take a z standard normal, I'm going to square it, and I want to see what the distribution would look like. Well, that implies that z is equal to plus or minus the square root of x. Okay, just using the property of square roots. So here, remember, z is standard normal. We're going to omit the mathematical derivation because it uses change of variables, and lots of people get confused, so we're going to try to go for an intuitive approach, and hopefully this makes sense. Start off. First thing we know, x squared will never be negative, right? It's x squared. Any squared number is going to be positive. So the probability that it's less than or equal to 0 is equal to 0. So here I put in, here's the probability it's less than or equal to 0 would be right there. And I put his point down here, 0, 0. Now, what if x squared is equal to 0.1? Well, this corresponds to z being between negative 0.316 and 0.316, and notice the big jump in probability there. Okay, and that's going to be important later. There's a big jump in probability. And then if I keep going with this, you can see what happens when I go to 0.2. There's another jump, but it's not nearly as big. And if I keep going, you can see it slowly increase. So here we're at 0.5, and we've got a lot of the area under that curve already taken care of. But notice that the jumps are becoming less and less. Here we put in all the dots by 0.1 out to 1, and you can see where we're at. Here we went out to 2, and it's slowly arcing over with a smaller and smaller increase every time. Until when we get out to about 6, it's really getting pretty flat out here. The increases are tinier and tinier and tinier. So this is what we're going to work with. This is the area, right? These are the areas that we're finding over here. Okay, so I've filled in this with a whole bunch of points. This is this chi-squared Cdf. There's secretly a line hiding under this. This is the PDF. Now you have to remember the PDF is the instantaneous rate of change of the CDF, right? So it's the slope of the line tangent to the CDF. And if I notice right here, from here to here, at this very little edge here, this slope is really high. So I would expect this value to be really high. And as we go along here, the slopes are going to decrease until they start to flatten out. And notice they decrease drastically, and then they start flattening out, which is exactly what I would expect them to do. Now this is known as a chi-squared with 1 degree of freedom. There are going to be more chi-squareds floating around. They're going to have lots of degrees of freedom. But right now we're just going to focus on this one. Okay, so here, a chi-squared with new degrees of freedom, and the previous one it was 1, but later we'll figure out how to get more, is given by, and here's this formula, 2 to the nu over 2, gamma to the nu over 2, x to the nu over 2 minus 1, e to the minus x over 2. When x is greater than 0, and it's 0 if x is less than 0. If I stare at that, we've seen this before. A formula looked very similar to this. If I look at the gamma distribution, I have something here, a number to a power. I have a number to a power. I have the gamma function with a number inside. I have a gamma function with a number inside. I have an x with some number minus 1. Here I have an x to this some number minus 1. And then I have e to the negative x divided by some number. I have the same structure here. So this isn't something as new as we thought it would be. This is a gamma distribution with alpha equal to nu over 2 and beta equal to 2. See, if you just swap in 2 here for beta, every place there's a beta, you'll see that it maps directly. Every place there's an alpha, put a nu over 2, and you'll see it matches up perfectly. All right, so that means we don't have to work very hard to get the mean and the variance. Okay, so for the mean, we know for the gamma distribution is alpha beta. Well, alpha is nu over 2, beta is equal to 2, 2's cancel, equal to nu. Sigma squared, alpha beta squared, nu over 2 times 2 squared, one of the 2's cancels, and we ended up with 2 nu. All right, so to finish this off, right now the CDF is too complicated, right? We omitted it for the gamma, so there's no point in talking about it here. But we'll use a computer later when we talk about this again in a couple videos. Right now, I'm just trying to get you the idea that we are interested in taking variables like standard normals and transforming them into something else so that we can create new variables, new random variables, so that when we look at our test statistics, we'll know what distribution they follow, or at least approximately follow. And that's our motivation behind this. So we're going to move on to the t-distribution next. See you there.